Despite ruling the seas for millions of years, the Ammonite legacy, like all good things, came to an end at the end of the Cretaceous-Tertiary mass extinction. The most likely cause of extinction was a combination of extreme environmental changes that occurred after the boloid impact on the Yucatan Peninsula. The boloid impact resulted in massive amounts of pollutants being scattered into the atmosphere and oceans. This caused temperature drops, reduction in light penetrating the atmosphere, and subsequently the water and oxygen content of the water. Lower oxygen meant more sensitive organisms began dying off. Competition for food skyrocketed as prey species died off. Among the 10 catastrophic extinctions of ammonites in history, at least 8 occurred during periods of elevated ocean acidity. During the final extinction, ocean acidity rose due to the massive amounts of carbon dioxide produced upon impact. A lot of this carbon dioxide eventually dissolved into the oceans. The acidity had a pronounced impact on ammonite shells and was even more detrimental to ammonite larvae. A close extant relative of ammonites, the nautiluses, were subject to the same conditions as ammonites but did not perish. How could these two morphologically similar organisms both have survived the Permian and End-Triassic mass extinctions, yet only nautiluses survived the Cretaceous-Tertiary extinction? The key determinant was the depth inhabited by the species. Deep-sea organisms were more likely to survive, and even today, undiscovered ancient life forms are most likely found in these depths. Ammonites fed in shallower waters than nautiluses, meaning nautilus's prey was impacted to a lesser extent. Nautilus also laid larger eggs and at lower depths. These larger, deeper-dwelling larvae are less exposed to the acidic, shallow water.
Our extensive knowledge of ammonites comes from studying their fossils, which are scattered all over the world. So how does an ammonite go from this to this? Once an ammonite dies, either naturally or through predation, its body falls to the seafloor, and the flesh, which is composed of soft tissue, quickly decomposes or is consumed by other marine animals, leaving behind only its shell, which is composed of a carbonate mineral called aragonite. This shell is eventually covered by fine sediments and becomes buried under the seabed. Over time, mineral-rich waters infiltrate into pores within the shell and replace the original shell material with minerals such as calcite or pyrite. After millions of years, the sea level falls enough for the seabed to be exposed, and erosion exposes the ammonite fossil at the surface. Another process by which ammonite fossils can be preserved is through the formation of internal molds. In this fossilization mechanism, surrounding sediments fill the shell cavity and harden over time to form a cast. The outer shell eventually erodes away, exposing the more erosion-resistant internal cast, which contains features and details of the outer shell. This concludes our presentation on ammonites. Be sure to check out the other exhibits at the museum. Thanks for watching.